Last time we finished construction of explicit expanders, and we started this new topic called pseudo random generators. We'll shorten it to PRG, and this will be the most important object in this course on randomized methods, because this you can think of as the way to generate random numbers efficiently. Okay, so in practice, if you want to simulate a coin toss, you want it to be efficient. So you can think of PRGs in that context. So first thing is, how do we formally define this object? What do we want from it? So what we want is that this S comma epsilon, there will be two parameters. S will be the resource which your PRG can fool. So in this case, it will be small sized circuits of size S. Epsilon will be error. Okay, how much is it able to fool? Ideally, we would want epsilon to be 0, because no circuit of size S should be able to distinguish between this distribution R and the uniform distribution UM. So ideally epsilon should be 0, but then we have to tolerate some error because of practical considerations, because of efficiency. So we'll allow epsilon to be something smaller than half, a constant. Okay, you can think of epsilon as 0.1. So first we define distribution. So a distribution R is called S comma epsilon pseudo random if any circuit of size S is unable to distinguish R from UM. Okay, so the probability of C being 1 on either of these distributions is very close. It is close by epsilon. It is epsilon close. So we can also write that. Okay, you can think of this notion of closeness. But remember that it is with respect to a limited resource, and that is size S circuits. Okay, and so what is a PRG now? Once you have defined pseudo random distribution, a PRG is an efficient, you can think of it as a circuit or an algorithm. It's an algorithm which can produce this distribution R. So let S be a function, a 2 raised to n time computable function, G, it is multi-valued. Okay, it's not a Boolean function, it's actually a function, is an SPRG if for all L, G stretches, so G stretches L bits to SL. Okay, so think of S as the stretch function for this PRG G. So it will stretch L bits to S of L bits, and if you look at G of UL, this is pseudo random. PRG is basically a function that is easy to compute, where easy is very relaxed. It is 2 raised to n time. So this is not, this is actually smaller than exponential, it's E, the class E and not the class X. But with that you have enough time to compute this. So G is easy to compute, and it will stretch a seed. So L seed it will stretch to SL, and then the output of G, if you look at the whole space, it will look more or less random. Two circuits of size S cube. Okay, so remember that the output you are getting is SL bits, and essentially in that much of size, circuits will be fooled. Okay, so circuits of size SL cube will be fooled, and then the error we are allowing is 0.1. It's not 0 exactly, but it's 0.1. These constants 3 and 0.1 are kind of arbitrary. We have picked them so that all the subsequent theorems work, but you can actually change them also. It's not something very specific. So what is the consequence of this definition and then this object? First question you should ask is whether this object actually exists. That is an open question currently. We don't know whether these things exist. And the problem is this time, 2 raised to n time computability. This kind of makes it explicit. So explicitness is the issue. If this condition of 2 raised to n time computability was not there, then we could show that actually random functions G will work. They will be able to fool, stretch and fool circuits, but then they will most likely be uncomputable. I mean, at least uncomputable in 2 raised to n time. So this 2 raised to n time is the important condition, and that is why we don't know whether they actually exist. If they exist, then we can actually de-randomize complexity classes. So what can you de-randomize? So remember that stretch is L to S of L. So basically any algorithm that requires that many bits, you can provide that randomized algorithm, this SPRG. Okay, so that will reduce the random bits from S of L, demand S of L to seed L. So if L is very small, then your algorithm will save the random bits. So SPRG saves random bits from S of L to L. That is the idea, and let us now show this as a theorem. How much is the saving, or which complexity classes are being de-randomized? So we will show so an SPRG exists. This implies that for every function L, BP time S of Ln can be de-randomized in. So brute force would have been 2 raised to S of Ln, because you have to essentially go over the whole space of random strings, but this PRG will make it much smaller. It will make it 2 raised to ln. Okay, so basically focus on this 2 raised to ln. So what you are getting from SPRG is 2 raised to S of L is being reduced to 2 raised to L, and this is happening because the random bits S of L is being reduced to random bits L by the stretch that the PRG gives. But of course, we have to see why exactly, what is this deterministic algorithm first of all, and why will it work, right? So that we will do by essentially by taking a majority vote, a trick that you have seen before also many times in fact. So the idea is use SPRG-G as the source of pseudo random bits in the randomized algorithm and take a majority vote. So the idea is that your randomized algorithm will be fooled. Gets fooled by G. That is how you can put it. So the randomized algorithm would not know whether it is getting random bits or pseudo random bits. But of course, this we have to now formalize what exactly is the, how exactly is this fooling happening. So language L is in BP time. If there exists an algorithm M, so a Turing machine, that on input X n bit input uses big O of S of L of n, right? These many random bits are and runs for that much time. So this algorithm M requires M random bits and also runs for a similar amount of time, and then it outputs an answer which will be correct with probability 3/4. So the output of M on X on the random bits R will match whether X is in L or not. So that I am denoting by L of X with probability at least 3/4. So that is the meaning of L being in BP time. We will now change this algorithm M by using G. So, the de-randomization idea is to use the SPRG, the one that exists from the hypothesis of the theorem, to produce R's. So, basically the algorithm is just this. On input X, our deterministic algorithm B goes over all Z 0 1 to the L computes M X G Z. So, remember G of Z will be stretching L bits to M bits. M we have defined as S of L, and yeah, let me make it precise. Let me just make it M is just this. Okay, so it will stretch G will stretch L bits to M bits, which is S of Ln, and then this randomized algorithm M will use this output of G, and then it outputs the majority vote. Okay, so overall Z, take the majority vote. If 0 appeared more, output 0. If 1 appeared more, output 1. So, the claim is that this deterministic algorithm B correctly solves L. Let us see that. So, we claim that the probability over Z that M x comma gz matches Lx, this is at least 3 by 4 minus 0.1, which is more than half. We want to show that over the z's the probability is more than half, which means that the majority vote is correct. Okay, so the answer of B is correct, implying that B works. So, suppose this probability estimate is wrong, suppose not. Then the probability is less than 3/4 minus 0.1, which means that the probability over z of m x comma gz being equal to Lx minus the probability over R of mx comma R equal to Lx. This probability difference that m runs using G and m runs without using G. This difference is large, right, because you are saying on one hand that probability over Z is less than 3/4 minus 0.1. On the other hand, you are saying probability over R is more than 3/4. So, this is larger than 3/4 minus 0.1 minus 3/4, which is equal to 0.1. So, this means that M is able to distinguish between Z and R, right. That should be a warning sign. The way we define G, nothing should be able to distinguish its output from random. but here it seems that there is a distinguisher. So, to make this formal, you have to talk about a circuit, right, because SPRG was defined by a circuit. M is not a circuit, it is an algorithm. So, let us make it into a circuit. So, consider the circuit Cx. X is something fixed. In this argument, we are looking at X as fixed. That on input Y, outputs 1, if and only if M x y is equal to Lx. Okay, so Y are kind of the good strings, good random strings. This is what Cx is identifying, and as an exercise show that since M is S of L of n time, let us say Turing machine, we can simulate it by a circuit Cx of size square of that. Okay, so whatever is the time complexity of the Turing machine, basically every transition step of the Turing machine you can simulate by these AND or NOT gates, and the overall size you can easily show is at most quadratic. In fact, you can show something better also, but for us quadratic is fine. So, basically there is a circuit Cx which on Y is correct, its value is L of x for all these y's in the domain. So, what this means is that Cx can distinguish G of u ln from u of s ln, the uniform distributions. Okay, so U denotes a uniform distribution of appropriate size, and G of UL you can distinguish it from U of SL using Cx, right, because we have assumed that the probability difference is larger than 0.1. So, this is what we are using, and that is contradicting the definition of SPRG G. So, this contradicts contradiction to the definition of SPRG G, which means that actually the probability difference is small. So, it is as shown before more than half, okay, as claimed before. This implies that the probability over Z of M x G Z being Lx is greater than half, which means that majority vote works, which means that B is correct. B solves L correctly in how much time? So in the definition of B, remember in this definition, green definition, it is going over all the z's, right? So that's 2 raised to ln. And the time complexity is that of m. So that's S of ln. Okay, so this is how you use an SPRG. You can de-randomize, and equivalently you can reduce the number of random bits. So now to see the impact of this observation, let us look at various parameters or parameter settings for the stretch S. So by picking various stretch functions S, we get the following conditional de-randomizations. Conditional because I mean you have to assume that an SPRG exists, right? Those questions we don't have an answer for currently, but nevertheless this even conditional de-randomizations are quite instructive in the sense they will tell you what SPRG do you need. So to get BPP equal to P, so if there is an exponential stretch PRG, then BPP is equal to P. Okay, so that's an exponential stretch. Which means that L you are stretching to 2 raised to order L. Okay, this is the maximum you can hope. You cannot do more than this. So if you can really construct optimal stretch PRG, then you can solve any randomized algorithm. You can make it deterministic, polynomial time. If there exists 2 raised to L raised to epsilon PRG, then BPP you will put in quasi P. So this is slightly more than polynomial time. This is 2 raised to poly log n. And the stretch that this is demanding is not exponential, it's we call 2 raised to epsilon L exponential. This here now you can use, for example, 2 raised to square root L or 2 raised to cube root L stretch. So you can call it sub exponential. And the weakest stretch you can hope for is like quadratic stretch, cubic stretch, polynomial stretch. So if there exists L to the C PRG, for c greater than 1. Then what happens? Even then something happens. So BPP then would be in sub exp. Like we defined before. Okay, so you go to P or you go to quasi P or you go to sub exp. This is polynomial stretch. One important thing I forgot is I have to add here for every C. For every C, if you have an L to the C PRG, only then. So we will prove this quite simply using invoking the previous theorem. It will also imply that for every C there is an L to the C PRG, and in that case you can put BPP in sub exp. Okay, so what is the proof of all this? The proofs will be similar. You just have to say what basically in this lemma that we had, what is S, what is L, and then look at the RHS. What is 2 raised to L? Okay, that's all. That's all you have to check. So we'll say apply the lemma. On S and L. So first you apply it. S is in this case the function that sends n to 2 raised to epsilon n. Okay, that's exponential. And L is the function that sends n to C log n. Okay, so since you have in condition in this item 1, you are assuming that there is a exponential stretch 2 raised to epsilon L PRG. So that is why the stretch n to 2 raised to epsilon n is possible. And then when you apply this S on L, right, you will see that you will get the following. So 2 raised to L of n is equal to n to the C, and S of L of n is equal to S of C log n, which is equal to 2 raised to epsilon C log n, which is n to the C epsilon. So both 2 raised to ln and S of ln, they are both polynomial in n. So in the lemma statement, LHS S of so BP time n to the epsilon C, this is being put in D time n to the C times the same thing, n to the epsilon C. Okay, and the assumption was that there is an SPRG. So that stretch function immediately gives you the BP time D time connection, and the same thing you do for other items 2 and 3. So here you will pick S to be n to 2 raised to n to the epsilon, because that is what PRG you are promised, and L will be so L here, remember that in this proof L is always kind of the inverse of S. So here you can pick L to be C times log n to the 1 over epsilon. So when you compose S with L, you will see that you will get polynomial in N. That's the idea. And in the third case, S will be polynomial stretching n to the C, and L will be kind of the inverse. So this will be n to the epsilon. Okay, so L is always kind of the inverse of S. L is inverse of S. So based on that principle, we can show the collapse of BPP, right? BPP is BP time poly n, and depending on what kind of a stretch you have, you can put it either in P or quasi P or sub exp. Even sub exp is very non-trivial. All these are open questions on their own. So as you know, BPP in sub exp is an open question. We don't know the proof of this. And in fact, we believe that BPP is in P. Okay, so what this previous connection is showing, this corollary in blue is showing, is all these stretch PRGs, these are also open questions. Okay, we don't know whether they exist. So how do we construct these PRGs? So the only known way, we obviously will not be able to construct them in this course. Unconditionally, we will not be able to do that, but we will relate this problem to the problem of hardness. Okay, so that in itself will be an amazing connection. We will show that if there are hard problems, then these PRGs will exist, and then all these de-randomizations would happen. So the only known way is to exploit the hardness of problems. So what kind of hardness will suffice, and then what is the proof of this connection? So let us move to that. So hardness, PRGs, and de-randomizations are all open. And highly related. Okay, this is what we will now see, and we will spend the remaining course on these connections. You have already seen this easy connection from PRG to de-randomization. Now we will move on to the harder connection, which is between hardness and PRGs. And this hardness also, to be useful, it has to be for explicit functions. So it should be explicit hardness. Okay, that is why it is challenging. So actually we know that there are hard problems, like halting problem is hard, SAT is I mean, we don't know whether SAT is hard, but at least you know that halting problem is hard, and problems which are in EXP, you know there is a problem which cannot be solved in polynomial time. So that kind of hardness you already have, but the thing is we want more explicit hardness. So let us now get deeper into this. So hardness and PRGs. We define two types of hardness. Of Boolean functions. I should say here actually the focus will be not so much on explicit but circuit hardness. I should say that. So you have to show hardness in terms of Boolean circuits. It's not this P versus X or P versus E. Okay, this is in a way stronger. So the first definition is average case hardness, and the second will be worst case hardness. So for a function, Boolean function, the average case hardness will denoted by H average of F. This is the largest S. Now I am using the same symbol S like stretch, and later on we will see that actually this is because of this is for a reason. But again, a function S will be called the average case hardness of F, Boolean function F, such that every circuit for every circuit Cn of size Sn, for every circuit Cn of size Sn, Cn will not be able to solve F very well. So in other words, the probability of Cnx being equal to Fx on x un, so 0 1 to the n uniform distribution. If you just did a random choice or picked 0 or 1, yes or no in a random way, then probability would have been around half or at least half. And this circuit Cn is not able to do much better. That is what we want to say. So we will say half plus 1 over S of n. So this you can see as the advantage. So we say that F is average case hard, or F has average case hardness S if circuits of size S cannot give you advantage more than 1 by S, or they have advantage less than 1 by S. Okay, so half is for free just by tossing a coin and giving the answer, but nothing better these circuits are able to do, or not much better. Okay, so So that largest S is what you will pick. Notice that as you will increase the size S, as you will increase the size of the circuit Cn, Cn will start approximating F better and better on more and more inputs. Okay, so advantage will actually increase. So which is why saying largest is fine, because this largest will exist. It's not unbounded. And second notion will be worst case hardness. So we'll denote it by H worst F. This is again the largest S. Such that for every circuit of size Sn, now you want in worst case actually you want to be correct on every x. Okay, so we'll say that these circuits Cn are not able to, or they make some mistake, at least one mistake. So probability less than 1. That's all. Okay, so here even a single mistake is considered a failure. So what is the largest S circuits that will be a failure for computing F? Right. So that will of course is expected to be bigger than the average case hardness. Okay, so you can write the relationship quite easily amongst these two notions. So the average case hardness is at most worst case hardness, which is at most. So average case hardness, note that this random choice thing already gives you half, right? So if you take the size to be more than 2 raised to n, then you can just use the truth table of the function and you can exactly compute f. So this is less than 2 raised to n. It cannot exceed 2 raised to n by truth table of f. And yeah, the size when you convert truth table to circuit, that may be slightly more than 2 raised to n. So maybe we make it a bit more. Let's make it 2n. Okay, in that much. So worst case hardness, obviously it cannot exceed much more than exponential in n, and average case hardness will be smaller. Okay, so obviously the open questions here will be then can you bring the worst case hardness close to this upper bound? Okay, can you bring it close to 2 raised to 2n? So number of functions on 0, 1 to the n. This will be how much? 2 raised to 2 raised to n? While number of circuits of size n is around n to the n. So, you have n gates and each has fan in n and fan out also at most n. So, you can see that the way you can arrange the gates is something like n to the, let us say, 2n, which is much smaller than 2 raised to 2n, right. So, this means that usually for random f, the worst case hardness is, let me actually, I have to replace this by some size. Let me replace it by size s. So, this is something like s to the 2s, which you can make much smaller than 2 raised to 2n if you take s to be sufficiently smaller than 2 raised to n. Let us say I take 2 raised to n by 2. If I take s to be less than 2 raised to n by 2, then you can see that this inequality holds, s raised to 2s is less. So, number of circuits is actually much smaller than the number of functions of this much size. So, from that you can see that for random functions, worst case hardness will be this s, which is 2 raised to n by 2. So, generally functions are supposed to be pretty hard in terms of Boolean circuits, but what we do not know, of natural functions. Or explicit f with super polynomial hardness. So, actually we will be interested in these explicit functions with super polynomial hardness, in the ideal case exponential hardness. Okay, and then we will relate that to we will relate it to construction of PRGs, and then from PRGs you will get the de-randomizations.